So this is the Sn2 review, and I'll just go down the list and then show you a lot of different problems with Sn2. First thing is that Sn2 usually just does primary and secondary carbons. That's where it attacks. You'll rarely see a tertiary carbon having an Sn2 reaction. Next thing is that it needs a strong nucleophile with these nucleophiles. It prefers aprotic solvents because, see, when you have a aprotic solvent, it doesn't donate a hydrogen to the strong nucleophile because you want that negative charge on that atom, because that negative charge means that it can donate another electron to another electrophile. But if you have a protic solvent, the protic solvent will donate a hydrogen and make this a weak nucleophile, and that's not what we want. We want a strong nucleophile for Sn2, and that's why aprotic solvents will help speed up the reaction. So the next thing is bimolecular reaction. That's what the 2 stands for in Sn2. Bimolecular means that it depends on both the nucleophile and the electrophile. So if they asked you a question saying if they increased the concentration of the nucleophile, it would impact the speed of Sn2. It would increase it because it's a bimolecular reaction, right? The Sn2 part, the 2 part. And therefore, it would impact the speed of the Sn2 reaction. A key thing that a lot of people forget, and it's a very common mistake, is inversion. So when the and I'll show an example, but when the nucleophile attacks, and if that carbon has stereochemistry, it will actually flip, because Sn2 is a back-attacking a reaction. So it attacks from behind, and therefore the stereochemistry will change. The other thing about Sn2 is that sterics will impede the speed of Sn2. And that's why an exception to this rule is just because it's a primary doesn't mean it will always happen, because if the primary is next to a quaternary, right, the quaternary will actually block the nucleophile from attacking the site, right? Because if you have a huge electrophile blocking the carbon, right, it'll have a hard time attacking that carbon because the sterics are impeding it, and sterics are just carbon groups or other structures in the way, large structures that are stopping the compound from attacking it. And remember, these compounds are rotating in the solvent, right? Because they're 3D organic structures, so they're rotating all the time. And so if it's really large, the nucleophile will have a hard time hitting the carbon because of the big group. Next thing is leaving group, right? So leaving group in the Sn2 reaction, the nucleophile will attack the carbon, and the leaving group will leave. So the better the leaving group is, the faster the Sn2 reaction will be. And finally, no carbocation rearrangements. Because in Sn1, you can have methyl or hydride shifts, but in Sn2, it all happens simultaneously. So therefore, you won't have any carbocation rearrangements. So now going to the problems, right? So this is a ranking problem. So try this first, and then I'll tell you the answer. And just rank it from 1 being the fastest Sn2 to 5 being the slowest Sn2. Okay, so to explain this, what we have is, well, I'll just show the answers first. So what we have here, right, is going through it. First, we look through if it's primary or secondary or tertiary. So this one is primary, right, because the site it will attack is next to the leaving group. So combining all of this knowledge in these problems will help you get the correct answer. So combining all this knowledge, well, the first thing is leaving group, right? So the leaving group is where the nucleophile will attack. So it'll be this. So we want to look at this carbon right here. So it would be the carbon that's next to the leaving group. So the next thing is we know that it prefers primary and secondary. So then we're going to label it. So I labeled it primary, right? Because this is primary, it's attached to 1 carbon. This one would be secondary, this one also is secondary, and this one is primary. So now we have that. Next thing we do is look at what type of leaving group it is, right? So for this, it's bromine, iodine, bromine, bromine, iodine. Now leaving group ability increases as you go down the group. So what that means is that bromine is a better leaving group than chlorine, iodine is a better leaving group than bromine. So it just increases as you go down the group. So that means that iodine, right? Iodine will be a better leaving group than bromine. So we write all of our leaving groups: bromine, iodine, bromine, bromine, iodine. So now, and the final thing is the exception, right? The exception to the rule, which is even if it's primary, sterics will impede it, and that's why if it's next to a quaternary, Sn2 will most likely not happen. So here, right, so even though this is a primary and it looks like it would be really high up, it ends up becoming 5, right? The worst, the slowest Sn2 reaction, because this is next to a quaternary, right? Because this carbon right here is connected to 4 different other carbons. So it's connected to a quaternary. So that will actually be 5, right? Because that will be the worst Sn2 reaction, because it's next to a quaternary, because the sterics will impede it. So now, since we have the exceptions out of the way, we can just look at the numbers. So we said that primary is preferred over secondary. So we only have one primary, and the leaving group's really good, so that will be number 1. Next thing is all of these are secondary, right? So what do we decided on? Well, we decided on the leaving group, right? The next choice is leaving group. Iodine is a better leaving group than bromine, so this will be 2. And now we have 2 of the same, right? We have the same carbon, meaning both of them are secondary. We have the same leaving group, both of them are bromine. Now what do we do? Now we finally look at sterics. So sterics will be what is to the left or right of that carbon, right? So this carbon, right, is next to 2 primaries, so we'll put primary. This carbon is next to a primary and a tertiary, right, because this is connected to 3, so it's connected to a tertiary. Now we look at the biggest, right? So both of these were primary. This has 1 primary and 1 tertiary. So now sterics come into play, and sterics just mean how big is the group next to the leaving group. So this will actually block the way of an incoming nucleophile, right? Because remember that this is in solution, this is a compound, and so it'll be rotating. So if a nucleophile tries to come along, right, and attack this carbon, this might end up getting in the way because it's so big, right? Because this is a carbon attached with 3 hydrogens, and this is a carbon attached with 3 hydrogens. Nucleophile comes along, this huge group might end up hitting that nucleophile. However, here, right, there's not that many, right? Because there's only 2. So this has a better chance of having an Sn2 reaction happen than this one. So therefore, this will be 3 and this will be 4. So the order is look at the carbon first, right? So it'll be carbon, look at the carbons first, then leaving group, and then look out for exceptions to the rule. So that'd be the quaternary exception. And then finally, look at sterics. So once again, look at the carbon, so primary, secondary, tertiary. Then look at leaving group. Leaving group ability goes down or increases as you go down. Finally, look for exceptions, and then the final thing, the final criteria you look for is sterics, which is why this one would be 4 and this one would be 3, because this one is a tertiary and these 2 are primaries. Now moving on. So let's say we have this compound, right? We have these 2 compounds in solution. So this NaCN, Na is just a metal ion, right? And so it doesn't really affect the reaction. So this is actually the real nucleophile. So it'll be because it has a negative charge. So this is our nucleophile because the negative charge is on a carbon, meaning that's unstable, so it wants to give those electrons away. So this will attack the leaving group on this group, right? So there's all of these are carbons which are pretty stable, but the bromine can handle the charge, so this nucleophile will attack right here. So the general concept for these reaction questions is look for which one is the nucleophile, right? And the nucleophile will be the one that wants to give away electrons. So this one doesn't have any electrons to give away, right? Because there's nothing on it that can attack. But this one has a negative charge on a carbon, making it unstable, so this one wants to attack something. Over here, on the electrophile, what you look for is the electron deficient area, right? So we have a really electronegative atom, right? What is it going to do? It's going to pull in electrons. So if it pulls in electrons, right, from here, that would make this area a little more negative, and this area, right, a little more positive. So a nucleophile wants to give away electrons to an area that's positive, right? Negative and positive attract. So this negative will attack this partially positive place because the bromine is pulling away the electrons toward itself. And then the bromine will leave because it's stable with the negative charge. And so this will attack here and then become this compound. Notice how this becomes a wedge and this becomes, this was a dash and this becomes a wedge. So what that means is, let's think about the 3D element, right? So the dashes mean that it's going into the page. So when this nucleophile attacks, right, if it's going into the page, there's nothing in this space, right? Or there's a hydrogen, but there's not really resistance in this space. So it's better off attacking from the front, right? If it attacks directly here, right? Well, if it attacks from the front, then it'll end up becoming a wedge because now it's sticking out of the page. That might be a little hard to see on paper, so it'd be better if you had a model so you can see exactly how it works. So the next example is a little bit tricky because of the fact that usually they give the nucleophile right here, and usually they put the electrophile right here. In this case, I switched it, and I also did something else. I made the nucleophile have stereochemistry. So in this example, right, the electrophile had stereochemistry, and so when it attacked it, it would create stereochemistry difference. It would become a wedge, right? But in this case, if the nucleophile has stereochemistry, it actually doesn't affect the stereochemistry of the end product. It remains a wedge, and that's because this part isn't leaving, right? It's not this carbon that's being attacked. It's this carbon over here. So that carbon, since you're attacking this one, it doesn't affect the stereochemistry of the existing nucleophile. So what will happen is the negative charge, and how you know that this is the nucleophile instead of this one, right, is because this has a negative charge. And so always look for the negative charge and look for a leaving group. So since this, and even if it doesn't have a negative charge or a negative sign, look for something that has electrons that can donate. So for example, in this case, we have the negative charge on oxygen that wants to give away electrons, right? So this will attack right here because iodine is a good leaving group, right? This is why you should memorize good leaving groups. So since we know iodine's a good leaving group, we know that this will be a little positive. It'll be partially positive, and over here it will be partially negative. Because iodine's also electronegative, so it'll be pulling electrons away, making this side a little negative, making this side a little positive. So negative and positive attract. So the negative will attack right here, and that's why it forms the carbon, and the electrons will leave to the iodine, and the iodine will go off. And so your final product will look like this. It'll have the carbon attached. Always count your carbons, right? So we have one carbon here, and so we added one carbon there. So moving on. So for this, we actually have it in Fischer projection form. So I'm trying to show you as many different combinations that they can throw at you, because the actual concept is pretty easy, but the way they present it might be a little tricky. For example, they might present it in a Fischer projection and then ask you the same thing. Will be a Sn2 reaction, E1, Sn1. But in this case, you know that's Sn1. All you have to do is figure out what happens. So in this case, what happens is that we know that this is a strong nucleophile, right? Because we have a negative charge on the sulfur. And now we have to figure out where it will attack. So the first thing you want to do is, since we know this is the nucleophile, this has to be the electrophile. Now we just have to find the right or the best spot for it to attack. So that would be right here, right? Because the bromine is a good leaving group. Nothing else is a good leaving group. So this carbon would be the one we attack. But how do we show that, right? How do we get this product? So what I show is how to actually see this in 3D form, right? So this is the Fischer projection. So that means that the horizontal lines mean that it's coming out of the page, and then the CH3 means that it's going into the page. The vertical lines mean that it's going into the page, but the horizontal lines mean that it's coming out of the page. So if you looked at the structure from the left, right? For example, if you were here and looking at the structure right here, right? It would look like this. So if both of these are coming out of the page, if you're looking at it vertically, well, from the side, the bromine would be sticking out towards you, and the hydrogen would be sticking out away from you. So now the CH3S minus is the nucleophile. It will attack right here, right? And so the bromine will go off. It'll leave. And this isn't supposed to be a half arrow. It's actually supposed to be a full arrow. It just looks like that. Yeah. So moving on. So once it attacks, we have the methyl group, right? The methyl group will go up, so it will become the wedge. We have the CH3S become in the plane of the page, and then you can rotate it, right? Because we need to put it in Fischer projection form. We can rotate the entire thing. So the SCH3 will be right here, right? If we, for example, if we moved it counterclockwise, it'd be SCH3 right here. The methyl group would come down, so it'll be in the plane of the page. And then finally, hydrogen would be sticking out of the page. So the final product would look like that. And so now, since we have to put into Fischer projection, we'd have the vertical lines, and then we'd have these sticking out. Because in Fischer projection form, both of these are sticking out of the page. And so in this case, since we're looking at it from the side, it's the SCH3 is going away, but if we look at it vertically, it would look like this. So the next problem, we have this. We have this structure, and then oxygen, and then we have two things, NaH and then CH3I. So NaH, well, first we have to identify what NaH does. So Na is +1, H, that would mean that H has to be minus, right? So now we identified our nucleophile because if there's a negative charge, that means it wants to attack something. So in this case, this is something you can memorize, but NaH always will take away a hydrogen, right? So it will always take away a hydrogen. So this will take away this hydrogen, and the hydrogen electrons will go towards the oxygen. That means that the oxygen now will have a negative charge, right? The oxygen will have a negative charge right here. Now the next thing, the second part of the chemical reaction is we have CH3 and I. Remember that I is a good leaving group, right? So this will be partially negative and this will be partially positive. Negative and positive attract, so this will attack right here. And so it will attack right here, and then therefore it will form a bond, and then these electrons will go to the iodine, and then that will be the leaving group. So the final product will look like this. It will have your original structure, and then have the carbon, right? Because there's one carbon here, so one carbon here, sticking out from the oxygen. So next problem, we have this. We have this original structure. There's two places where there's stereochemistry, and then we have NaN3 minus, because Na, right, is +1, so N3 would be minus, because they have to cancel, so because there's no charge on the original formula, so this would be N3 minus. Now since we know that N3 minus is the nucleophile, and plus it has a aprotic solvent, that means that it's definitely Sn2, and secondary, right, because it's not this one's not tertiary. So we can use this to attack this side, right? And once we attack it, the electrons will go from this bond to the bromine, and therefore we will have the inversion where the wedge becomes a dash. Now notice how the stereochemistry of this doesn't change, right? Because the nucleophile only attacks one place. It doesn't attack this place, therefore the stereochemistry of this does not change. So for this one, we have an interesting one, right? So we have this compound, which will be the electrophile, right? In this reaction, and like I just said, NaH, what you can memorize is that it takes away a bromine. So in this case, the Br, right? The Br doesn't have a hydrogen. that means it has to take the hydrogen away from the nitrogen. So the NaH, right, it'll take away the hydrogen from the nitrogen and form two lone pairs, and it'll form a negative charge. Now it's not done, right? It's not done yet, because this now has a negative charge, and right here it's partially positive, here it's partially negative. So this negative will actually attack this carbon right here. The electrons will go to the bromine, and that will be the leaving group. And so now you actually have a ring form, right? So originally the structure was open, but after all of this, the ring actually closes, and you end up with a neutral nitrogen. So that was a lot of different examples, and hopefully I covered many of the different types of Sn2 reactions. And just keep doing a lot of different practice problems, so therefore the knowledge and the skills will become really concrete. So I hope that helped, and thanks for watching.